In lecture 5, I will talk about principal curvatures and tell you about the Gauss-Bonnet theorem, and then just mention what a Lie derivative is, killing vectors are, and then go on to talk about finally what tensors are. And then in the second half of today's lecture, I'll talk about one forms, two forms, p forms, and then we'll see where it goes from there. So this is the end of the 19th century when Gauss comes up with how to characterize surfaces. And of course, naturally, we look at two-dimensional surfaces, and we live in a three-dimensional world. So there is an intrinsic and an extrinsic curvature. Extrinsic is what you see from outside. Intrinsic is what you see while living on the manifold itself. So intrinsic is what an ant sees. Extrinsic is what a super being like us sees. Why is this important? Because we live in a four-dimensional world, and we would like to know whether we live in a flat universe or in a universe that is curved. Now, we can't go to the fifth dimension. We can't ask somebody up there, is there, if there's somebody up there, that are we curved or not? No, we have to discover this for ourselves. And how do we discover it? Well, for that, we need the techniques of differential geometry. Okay, so this is what Gauss said. He said there are two numbers, K1, K2, and these are the principal curvatures. These can be found intrinsically by an ant which is crawling around. He relates it, well, Riemann came along and then he was able to relate it to the Riemann tensor, which we discussed last time. The Riemann tensor then reduces to the Ricci tensor, which reduces to the curvature R. And I won't give the formula for that, but from the Ricci tensor, from the Riemann tensor, you can get both of these as well. But what we need now in this very superficial lecture, because I'm not going to go into any details, we went into what the Riemann tensor was and covariant derivatives and all that last time, but now things are going to become too advanced for us to absorb in detail. So what I want to show you is pictures. And these pictures are from Wikipedia. So everybody can go and get these, look at these from there. जोहेब जब मैं बोल रहा हूँ जब पिक्चर आएगी तो मुझे ना दिखाना बस इस पर इन्हें concentrate. So here are three surfaces, a sphere, a cylinder, and a hyperboloid. The sphere has got two curvatures, but they're both the same because the sphere is, of course, spherically symmetric. If you're sitting at a point, then it looks the same whether you look sideways, this way, that way, or up or down. So here we have a situation where both K1, kappa 1 and kappa 2 are the same. And in fact, if you calculate kappa 1 or kappa 2, the answer is 1 over the radius of that sphere. The bigger the sphere, the flatter it is. Now let's come to the cylinder. The cylinder is flat in one direction, it's curved in the other. Where it is flat, the principal curvature is 0. So if you travel, in this case, upwards or downwards, it's flat. your basis vectors will not change as you go up or down. And so one of these curvatures is 0. Hence, their product will also be 0. And now let's look at the third one, which is the hyperboloid. You stand anywhere on this. Now you can see that it curves upwards in one direction. So if you go up or down, it curves differently than if you go sideways. So one of these curvatures is positive, the first one, and the other one is negative. Okay, how do we determine these curvatures? Next slide. Each point on the manifold has a tangent space to it, tangent plane, which you can see. And we have defined what a tangent plane is. So if you take all possible curves that go through the point which is at the very center, which we call point P, then the set of all tangents at the point P, they form the tangent plane. Now, you can create a normal vector at each point P that is normal to the tangent plane, and then you can then draw two planes that intersect along that line and whose axis is the normal vector over here. These are the planes of principal curvatures. They are perpendicular to each other, and now you can see that for this case, which is the hyperboloid, in one case you go up, it's positive curvature, in the other case you go down, negative curvature. Next. But here is a case where a manifold has both positive and negative curvature. So you see, where there's positive curvature, you will see that it looks very much like a sphere, at least at the edges. On the other hand, you see that in the negative curvature, if you travel around the toroid, then it has positive curvature. But if you travel from the inside outwards, then it has negative curvature. Their product, kappa 1 times kappa 2, is negative. Next. This is the hyperboloid. And now you can see that if you were to draw a triangle on this, then you can see that the sum of the angles is less than 180. That parallel lines are diverging, and this is what they call a horse saddle, and it's an inflection point. There is an inflection point over there, right at the center. Next. And here is a situation where you have, okay, a sphere. Well, the toroid is shown for comparison, but here is a sphere whose ends are pinched and where there are singularities. Now at that point, at those 2 points, it is no longer a manifold. But that toroid is a manifold. So this is just to give you a qualitative indication of what Gauss did and how he was able to calculate curvatures and prove the theorem that I'm going to come to, which will make sense only in this context. All right, we're done. So Gauss defined this K and capital K then will be K is positive for a sphere, 0 for cylinder, and negative for a hyperboloid. Now remember one thing. Curvature is a local property. You are at a point P. At the point P where there is a tangent plane, you calculate your derivatives, okay? But that curvature can be different at different points on the manifold. Somewhere it is flattish, some other places it is more curved. What Gauss was able to prove was this very famous theorem. So this, remember, is a local quantity. And this is in this is the extrinsic. This is calculated from extrinsic calculations. So we are in 3D. K1, kappa 1, and kappa 2 are measured by ants. What he was able to prove was this: that suppose I integrate over the manifold this quantity K, which is the Gaussian curvature, then the answer is 2 pi times chi of m. This chi of m is called the Euler characteristic. And it is defined as 2 minus 2 g, where this g is what is called the genus. The genus is the number of holes. A sphere has no holes, and so this is 0. A torus has one hole, and so chi of m will be 0. So this is 2 minus 2, that means chi is 0. Let's see whether this tallies with what we have over here. So for a sphere, kappa 1 is kappa 2 equals 1 over, let's call it R naught.
Is this kappa?
Huh? Kappa 1. Kappa 1 equals kappa 2 equals 1 over R naught. R naught is the radius of the sphere. Well then, that says K is 1 over R naught squared. Then this dA, okay, dA. This is, so the, in this case, K is just a constant. So we can write this as area is 4 pi R naught squared, which is 4 pi. No big deal for a sphere. But what if you take the sphere and you start squeezing it? this holds even then. Now, this is the amazing thing, that it doesn't matter what is the precise shape of the thing that started off as a sphere. You started to hit it, squeeze it. In some places it goes down, some places it goes up. But the value 4 pi will not change. And that's the beauty of the theorem. So this is what is called a topological invariant. Even as you change the precise shape, you don't change its topology. That number remains 4 pi. Okay, so that's a very, very deep result. Now, what you saw over here was 3D looking into 2D. But what if you are in 4D looking into lower dimensions? Well, this generalizes there. In fact, it generalizes from any number of dimensions to lower dimensions. And so instead of you're having two tangent planes, instead of having the tangent plane and two planes meeting along a line, you will have 3 planes, but those 3 planes will be then in suitable dimensions. That's all I'm going to say over here. Unfortunately, this is a whole subject in itself. Any questions? Okay. Next. The last time I talked about the covariant derivative and made a definition that d mu v nu equals plus gamma and mu. Something like that, yeah? What was this covariant derivative? It was, of course, this is clear what this means. You take the difference in the values of v between two neighboring points, and then divide by the distance between them. And this was the Christoffel symbol, which is 0 on a flat space. Okay, now I'm going to, so that's one definition, and a very useful one, because from this we define what was this. And this gave us the Riemann definition of the Riemann curvature tensor, and then lots of properties come from this which we are not going to go into. But that was the covariant derivative. There is another derivative which is very important in general relativity, in differential geometry in general, and that is called the Lie derivative. Which is LV acting on something. Okay, first of all, let me say that this is a derivative with respect to a vector. This over here is a derivative with respect to a coordinate. Now, In fact, I should say V over here is not just a vector, it's a vector field. So what's the difference between a vector and a vector field? You know the answer, but if somebody tells me, that would be nice. Of course you know the answer. Yes, go ahead. What's the difference between a vector and a vector field? First of all, what is a field? Let's start from what is a field, just to refresh your memories.
Sir, we can say anything that has some value in space is called a field.
Very good.
And
So something that takes different values at different points on a manifold constitutes a field. Okay. Now what can be the character of that field? It can be a scalar,
yes,
scalar field,
yes, it can be
vector
both.
field, tensor field, and tensors are of a million different types.
Yes.
But those are all fields. Okay.
So now if we come to the vector and vector field, if we are saying just a vector, that means we are talking about a specific directed line segment. But when we are talking about a vector field, that means we are talking about a function whose outputs are vectors. So we give it an input and number, it gives output as a vector.
Right. So how would you, any other comments on that? Can you give me examples of vector fields?
So I think if we speak physically, gravitational.
Yeah, physical fields.
Gravitational fields, electric fields, they are.
Gravitational field? No. What do you mean gravitational field? No, not gravitational field. No. Something else which is more common, because the gravitational field is actually a tensor field. So I want to keep away from that. Give me a common everyday example of a vector field. Pichel.
Sir, we have electric field as a vector field and magnetic field.
Yeah.
And there can be other fields that we deal in physics. For example, velocity field when we are dealing with fluid dynamics.
Yeah. Okay. Right. So think of it as water which is flowing. Water will flow in a particular direction with a particular speed. So it's a vector. And so this over here, the Lie derivative is with respect to some vector field. Okay, now if LV acts upon a scalar, let's say that scalar, what should I call it? Phi, okay. Then it is so you could think of it as V dot gradient. I mean, that's one way of writing. This is one way of writing this V dot grad F. It's the directional derivative, exactly. Okay. But a scalar is very easy, because all you do is you look at the value of the scalar here, value of the scalar here, and you take their difference, no problem. But here, suppose I ask, here is a vector W. I'll put indices later. It's okay if the space is flat. You can just take that vector over there back. It will not change its direction. But if it's a curved space, then the vector over here will be pointing in a different direction from where it was here. And so I need now a different definition. I have to take this vector back to here, subtract the two vectors, and then divide by the small distance between them. Okay, so then this is defined differently. This is defined and this is defined now component by component. I can't do this without components. This is how it will be defined. What if there's a vector, if there's a tensor? Now here, if I want the, let's say the roth component, then I will define this as V sigma D sigma G mu nu. By the way, I didn't have to put G over here. Anything with two indices, so I could have put T over here, S over here, whatever. So just have to be careful on this. Then plus, let me see, I think one has to do this carefully. So I will define this. And also let me call this row. You see that the first term is exactly what we have over here, V dot this partial derivative, acting not on the vector W, but on the tensor here. And I'm going to tell you really what tensors are today. And then there are two G's and D acting on V, D acting on V. Because V is a vector field, it is different at different points. And we can now generalize this. Actually, suppose that this had mu, nu, sigma, well then D would, this partial derivative would act on this thing, and then all combinations later. Okay. Now this can that's the Lie derivative acting on this, and we can actually write this in a nicer way. We can, in fact, that's okay. This is fine. Now, so what the Lie derivative does, it takes the tensor, brings it back, compares the two, and then tells you what is the real rate of change of that quantity. So if this is not G, it is something else, it doesn't matter. But so in a sense, the Lie derivative tells you what happened. The Lie derivative is telling you go with the flow. जहां कोई चीज बह रही है उसके साथ साथ आप चलें. Then you pull it back and you compare it, and that will tell you the real rate of change. Now, the last time I proved to you that if you are traveling on a geodesic, then the vector that you're carrying with you doesn't change. Yeah, it is changing. There are two parts to the change of the vector. One is the change in the coefficients, but the other thing is the change in the basis vectors. And what I showed you that the parallel transported vector, the one that you hold in front of you, so in case of the car analogy that I gave you, you are holding onto your steering wheel and you're not moving it. So then you're traveling on a geodesic and you're doing parallel transport. If you travel on the geodesic, then your Lie derivative will be 0. All right, now there are, if one takes a metric, that metric might have symmetries. If it's a sphere, you see that it is highly symmetrical. A toroid has got symmetries. Every regular geometry will have some symmetries. There are particular directions that you can travel upon where the metric does not change. And those particular directions are known as killing vectors. So, this leads to the concept of isometry. An isometry is a transformation that leaves the metric unchanged. And what that means is that the Lie derivative with respect to a particular vector called the killing vector of G is equal to 0. This is the definition of the, so, okay, let me put it, let me put in the indices over here. This K is called the killing vector. Well, this is a bad joke, but you've all heard of killing fields, जहाँ लोग मारे जाते हैं. Okay, this got nothing to do with that. Killing was a mathematician. Now, if you write this in terms of write this in terms of the covariant derivative, then you can what I've done in the notes is actually calculated the killing vectors for a sphere. We just don't have enough time to go through that calculation, but basically what you need is the covariant derivative d and solve this equation. Covariant derivative is known if you know the Christoffel symbols. Christoffel symbols are known if you know the metric tensor. And so in this way you get the killing vectors for a sphere, and there are 3 of them. And they are actually quite simple, and you will recognize actually what they are. So there is remember that this is a killing vector field. There are going to be 3 killing vectors at each point on a sphere's manifold. Well, I'll call them KZ, which is now yeah. And then so we will now rotate z, x, y into y, z, x. And so z goes into y, x goes into z, y goes into x. And then we will rotate this still further. And here actually you can write these in polar coordinates, and you can write these in terms of E theta and E phi as well. And remember that E theta is d by d theta. This is, so you can easily make a change of transformations and get kz, ky, kx. In fact, this thing turns out to be just d by d phi. Kz will turn out to be just, because it's rotation around the z-axis. In quantum mechanics, you would call them generators of rotation around the x, y, and z axes. And no, there's no matrix over here. There's no matrix over here. This is, yeah, but polymatrices, those live in matrix space. Here we're talking of R3. Okay, so this is how, in principle, you can find the killing vector fields. Now, why is this important in general relativity? Because you then start understanding what it means to talk about the energy of the universe, for example. What is energy? As we have learned in school, energy is something that is conserved. Energy is something that does not change with time. Well, the problem is that time changes with proper time. Proper time is the correct way of doing general relativity. And that's an affine parameter. So if we know the killing vectors for a metric in general relativity, we know which direction to go so that things stay the same. That is to say, how you do measurements stays the same. Because otherwise, everything is changing, but if you go along the killing vectors, well, those are directions of symmetry. And so finding the killing vectors for a particular geometry in general relativity is then an important thing for general relativists to know. Any discussion on that? Because now I want to go on to something else. Now I want to go on to differential forms. So, and I'll tell you, this is quite confusing because of the notation. It's takes some thinking and some getting used to things, because the same symbol dx so confusing because dx can be a small number, so what are, if something is a number, what does that mean? That means you can add numbers together, you can multiply this by some other number, you can, you could say this forms a linear vector space. But then when it comes to multiplication, then you want numbers to commute. You want dx into dy to be the same as dy into dx. So one use of dx is as a small number. But the problem is that it can also denote a one form, which I'm going to define now. One forms you can add together, you can multiply by a number, still a one form. But the problem is that if I multiply two one forms together, then the order matters. This into that or that into this. And I don't know why these mathematicians, they had long debates and they finally said, no, we are going to use the same symbol. So I can't do anything about it. It's not my fault. But they use the same symbol. Okay, let's see. First of all, okay, so let's start our discussion. In an n-dim space, there are n one forms. If it's two-dimensional, then we say, we don't generally write dx1, dx2, we say dx dy. If it's 3, then dx dy dz, but they would still be forms. A form is a machine. Is a linear okay, when I say it's a machine, that means it's a linear operation. It's the same thing. I like machine better. That a one form, I should say, a one form is a machine that takes a vector as input and gives a number. So this is my machine. Let's call this either dx1, dx2 up till dxn. If I give this a vector e nu, which is a basis vector and which is the same as d nu, then out comes delta mu nu. So unless this and this are the same, you get 0. And if they're the same, you get 1. The way to represent this correctly is you say that dx mu operates on E nu and gives you know, it sort of makes sense. Because you have dx mu it's not that you can bring this over here and they will cancel, but it is sort of that. It's a rule. And the world is run by rules. We didn't make them. No, we made these ones. But that's how it is. So let's see how this works out. Let's take now let f be some function. Then from calculus, so this is now just, I'm going back to dx's being small numbers. So when we do calculus, we say okay, so this is then, because this is a number, I can take it here, there, whatever. And This is also what we call dx dot grad f. So the gradient of the function is the direction in which it is increasing fastest. When we dot it with that, we get a scalar. So for example, if this is the force, then this will be f dot dx. This will be the small amount of work that is done. All right, so that's, but on the other hand, we could write this as now I'm thinking of this as a form, and the form is eating a vector. And so this over, so then this is going to be something that acts upon f, but then this could be any f, so I could just remove it altogether. So now let's come to vectors and tensors finally. So what I've done is I have defined what a form is. But where does before I come to that, where do forms live? We know where vectors live. We have their house address. Where? A point P on the manifold where there's the tangent plane. So just as a vector belongs to or lives on T, P, M, a one form lives in the dual space T star M T. So just as many one forms exist as there are vectors, and of course there's one tangent space, one tangent plane at every point on the plane. Similarly, there's one dual tangent plane at every point on the manifold. Now from calculus, or rather I should say from the chain rule, how a different choice of coordinates for P in a change of partial derivatives. What I mean is the following. Point P, we can describe it as x1, x2, so if we use Cartesian coordinates, we can just say x, y, z, etc. Point P. But then P can also be and then you have this picture before you that these can be polar coordinates. You can use r, theta, phi, or you can use x, y, z. You can go one from one to the other or back from there to here. No problem about that. Well, suppose I do make that change, then d by d x mu prime is that's the chain rule. And what if I want to go the other way? By changing the prime. I don't even need to say that. So we can go you didn't stop me here. There is this very important prime over here which I missed. Okay, now I won't miss it. So what should I write over here? Let's call it nu. Doesn't matter what you call these dummy indices, right? So I can, this is the transformation when I go from x to x prime, and that's the other way around. Take any vector v. Well, that vector v is expandable by this. Then let's ask what this is. Well, this of course is, what have we called this? E prime mu. This is E mu, and this is E mu E prime mu. All right, so E mu prime क्या हुआ? Nu. Thank you, yes. So this is and x rho, let's say. Okay, but now we will define, we will require to transform oppositely. E mu or E mu prime, yeah, opposite to E mu prime. So when something transforms as the basis vectors, we say that basis vector transforms covariantly, and when it transforms oppositely, then we say it is contravariant. In that case, to continue this over here, this will be and then I will write this as it is, dx rho by dx prime mu d rho is just d rho. Okay, but now you see we have a contraction over here, mu, and the only way that these can be non-zero, okay, so I'm looking at this times this. In other words, I've moved this over here. This is just a number, and so this is equal to v rho d rho. That's the same as v over here. So we've done this before, I know, but the point is so important it had to be repeated, that a vector has a real physical existence, and even if you make a transformation within that tangent space, we're not leaving the tangent space. We're not going to a different point on the manifold. We're staying at point P. See, that was the whole point. You stay at the point P, but you describe it with different coordinates. Now this opens the door for definitions. Any question? No. A scalar is a tensor of rank. So, we deal, even temperature is a tensor. It's a scalar, but you can call it a tensor. A vector rank 1, 0. Why? Because E mu transforms in this way. That's the covariant way of doing it. Fine. Then tensor, let's see, let's call it V. In general, a tensor of rank transforms as m vectors. That are strung together. So if I have V, W, then V transforms as a vector, W transforms as a vector, then this will transform as two vectors. The tensor product means that this has got nothing to do with this. They're completely different things. If I have then there can be m of these, and this will be a rank M0 tensor. Abhi bata raha hu, abhi bata. I'll tell you. So I have to start now with what is 0, 1. Under a change of coordinates, under x goes to x prime on the tangent plane, on the dual tangent, dual space, a one form transforms like transforms contra variantly. In other words, and we will say that is a so dx mu, which is a one form, or a 0, 1 tensor. And then we can put a lot of one forms together, and it will give a 0n tensor of that type. So in this way, we can build all the tensors that we want. Any further question? Yeah. हाँ, ये So there's only one form, one form. And if I have two one forms and three and so forth, n of them, then that will be a tensor of that kind, because each one of them will transform oppositely, contravariantly. So this set of objects and that, all of those will transform oppositely. Let's look at, for example, a tensor G. Okay, now you see this doesn't have any indices over here, but when I make a transformation, then what will happen to this? This will go into dx prime mu, and this will go into dx prime nu, but this will transform like that. And this will transform as dx rho, dx sigma. And you see that then this thing will become well, this also becomes, I should have done this differently. Let me do this again. Each of these will change. Right? So now let's look over here. I have G nu prime there are too many news. Partial. Right. Now, this is the same as G mu nu because this is now transforming oppositely. Sigma. Yeah. G sigma rho transforms as this. So G goes to G prime, and G prime transforms in this way so that we get back the original thing over here. किसके ऊपर प्राइम है? ओ, इस पे नहीं है. हाँ. Yeah. Too many indices, but the answer is clear. So again, this is telling you that this thing over here is the thing that has, that is, it is the object. Yeah. Okay. Kya? So this G is a 0-2 tensor. A 2-2-2-0, yeah. नहीं. हाँ. तो ये टेंसर हमने इस तरह से बनाया. G mu nu transforms covariantly. Yeah. Yeah. So is a second rank covariant tensor. In the few minutes that I have left, I want to address the confusion that came about the last time. So G takes as, I defined I said that in the modern way of looking at things, G mu nu is equal to this. In other words, G is a tensor that takes as input two vectors, in this case unit vectors, and of course this E mu is it's the dot product of these two. And yeah, so and we actually use this for the Christoffel symbols. Now the confusion is this. So you ask me on the sphere, how does this work out? I'll say, let's go to even a simpler situation. Instead of the sphere, let us look at the circle. Circle is S1, we're in 3D, but we're in 2D, but we're just looking at the circle. Okay, so I have x squared plus y squared equals r squared. Then I make a change of coordinates, x is equal to r cos theta. I look at this. So if I look at ds squared, which is dx squared plus dy squared, well then we can see this is equal to, let's work that out again. So dx is dr cos theta minus r sin theta d theta. dy is dr sin theta plus r cos theta d theta. So in that case, dx squared is the square of this plus this, which is dr squared. The cross terms will cancel, and so there'll be r squared d theta squared. And so if we write this as g mu nu dx mu dx nu, how are we to understand this dx mu and nu? As small numbers, not as one forms. Then this is equal to grr dr squared plus g theta theta and so this thing is equal to 1 and this thing is equal to r squared. Okay. That's what we want, and you should have the same answer whether you use forms or vectors or whatever, but that was apparently not happening. Well, let's do d by d theta. This is d by dx. What is d by d? This is d by dx of theta is minus r sine theta. And this thing is, what do we call this? Ex. That's the vector in the x direction. And d by dy will be the same, except that you have r cosine theta dy. Okay. Now let's look at g of E theta, which is the dot product of the, there's only, so E theta is this, so this is dot the same thing. Well, that's r squared sine squared theta. And then from here, r squared cos squared theta. And the Ex dot Ey is 0, so this is equal to r squared. Now that's exactly the same as this. Let's check the others. G of RR. So well, then we'll have to write d by dr. Yeah, but you can easily do that. Huh? Yeah, it will come out to be 1. And the cross terms will come out to be 0. So any term like this, this will be 0. Just work it out. So you see, it does work out exactly as you expect. Your question was not about S1, it was about S2. But then it is exactly the same thing over there. There you have x equals r, x, y, z, polar coordinates, and you will have d by d theta, d by d phi, d by dr. Work them all out and you'll get exactly what you will get from this thing which we call ds squared. We've always called ds squared. So this modern way of doing things is not wrong. But it's good because it tells you that G is a thing that, of course, has to have coordinates, but it's really equivalent. Any questions? अच्छा, चलिए टाइम पूरा हो गया. Let's discuss that during the discussion session.